A very good morning to all of you, and today I'll be talking about the Dirac notation, which is probably the starting point of advanced quantum mechanics. The paper that we have in syllabi as Quantum Mechanics Second, and uh, this notation was given by Paul Dirac, and it's an abstract way of describing uh, the wave function. And uh, in quantum, first we have already talked about the wave function psi, and wave function. As we know, this wave function has no physical application and it has no physical interpretation, but it in itself is a mathematical function. And uh, the information about the state of the system, this information can be of the information about the position of the particle, it can be the information about the momentum of the particle. So any physically measurable information is there in the wave function, but this wave function, it's a complex function, and and it doesn't have the physical significance. And we know that this mathematical function contains all information about the system that we're supposed to understand, that we are supposed to have some state of understanding on. And if we take an example of particle in a box situation, what we did there, we obtained the wave function solving Schrodinger's wave equation. And the wave function that we obtained is an infinite array of sine of n pi by nx. Now this n can go on and on, so you can describe the overall wave function of this system as a linear combination of all the wave functions, is psi 1, psi 2, psi 3, and so on and so forth. Now, what is so important here is that this mathematical interpretation of the wave function is translated into a notation, what we call as Dirac notation. And in Dirac notation, what we have two important symbols, and these symbols carry the information. They carry the information as that of a wave function that we have in Schrodinger's picture. So what we have is we have a ket, and how do we represent a ket? A ket can be represented as psi or any abstract mathematical function, phi, or we can have a ket of spin up. We can have a ket of spin down. And what does this ket of psi represents? It can represent a state, or we may say an eigenstate. And there are a range of ways in which this state of the system can be carried out in terms of the ket of that state. Now, this ket can have, as we said, it can represent the spin of the particle. It can represent the column matrix. We can have a ket, say ket of psi, as a column matrix of A, B, and C. Now, if we talk about things analogous to this ket, in Schrodinger's picture, what we have is we have a wave function psi, and for psi we have its complex conjugate. We have its complex conjugate, and this complex conjugate gives us we take the complex of this wave function, which is basically a complex wave function. And when we take its complex conjugate and we make the product of the two functions, the product of the two functions lead us to what's called as probability density. And in the same way, in Dirac notation, what we have is for every ket, we have a dual. We also call it a dual. We have a dual, and this dual is known as, so this is my ket, this dual is known as the Bra. So this is the Bra. And in matrix notation, this Bra is the row matrix, but the elements that we have in the row matrix, we have to take the complex conjugate of these elements as A star, B star, and C star. So this way, what we have the mathematical abstract sense of the state of the system. And this mathematical abstract sense of this state of the system can be represented by this ket, and this ket can take all those observables. It can take an observable of position, it can take an observable of momentum, and things can be dealt in mathematical way to move on between the kets and bras. Now, in conventional, I would like to note that as conventional quantum mechanics, what we have is we have the wave function and the product of that wave function. Suppose I have a wave function psi, I make its multiplication with psi star, it leads to what is called as probability, the probability density. In a similar fashion, if we have to have the probability calculation for the state vector, what we do is we make use of inner product. Make use of inner product. Now, what is this inner product? We have the state of psi. This is the ket of the psi. Its dual is the bra of the psi, and the inner product between the bra of the psi and the ket of the psi leads to what's called as the probability density, in a sense that if the inner product between the ket of the psi and its bra, what makes it a Bra-Ket, if this product leads to 1, this is what is called as normalization. And if we have two different state vectors, now if I choose two different state vectors as, say, the state vector psi and say the state vector zeta, and if I take the inner product of these two, states, say zeta and psi, and this inner product comes out to be 0. And what does this tell us? If the inner product between the two states, the states psi and zeta, leads us to 0, it means that the two states are orthogonal to each other. The two states are perpendicular to each other. Or in other words, I can say it's impossible for the state psi, to evolve into the state of zeta. So this is how the inner product between the two state vectors to lead what's called as orthonormality. So it reflects the fact about the orthonormality of the two state vectors. And to begin with, if we go on here, let's give some philosophical meaning to what's this Dirac's bra and ket notations. So now, if I take this state psi that I was saying as a state vector psi, if I assume it's a musical note that we play, it's a musical note that's played on an instrument, and then the bra of the phi, which is another state vector, what it does basically is it listens to the musical note that's played by the care of psi. And when you calculate the inner product between the phi and psi, what it gives us is that it gives us the harmony that we perceive between these two state vectors, the state vector psi and the state vector phi. So we can begin to understand this mathematical abstract thing that we have in terms of 0 and 1, defining its defining the orthonormality of these two state vectors in terms of a musical tone. And when you take the inner product between a musical note, the care of psi, and listen it in terms of the bra of phi, we obtain a harmony between the two things that have been that the product that we have taken about. Now, another important analogy of this ket and bra notation that we have is if we take an example of throwing a ball. Suppose we have a ball, the ball is thrown into the air, and the throwing of this ball is represented by the care of psi, and there certainly has to have somebody who's going to catch this ball. And the person who is catching the ball, I represent the state of that person who's catching this ball by the bra of the phi. Now the two actions, the action of a ball being in the air and the action of a person who has caught the ball, the two, when you take the inner product of the two states, this inner product of the two states defines us whether there is a successful catch or not. That means if the ball is missed, then certainly you will have the missing inner product between phi and psi. But if the catch is a successful catch, it will the inner product will lead to that success that has been achieved by catching this ball. Now, let's take another example. Let's take an example of a student. Suppose we have a student, and if I represent the state of this student by a state psi, and certainly there has to have an examiner who will set a paper. So the student is preparing, he is choosing all the parameters to prepare his examination, okay, and then there's a person who sets the question paper for this student. Now, if I take the inner product of the exam question that has been asked and the knowledge of the student, which I represent by the care of the psi, and the inner product between phi and psi basically represents or determines the student's grade, that how to what precision there is a match between the question that has been asked by the teacher and the preparations and the answers that are given by the student in terms of that examination. So the inner product will decide the percentage of the percentage of the match between the two situations. And we can take another example of, suppose we have a giant white board, and think about this whiteboard having infinite rooms on this whiteboard, and what we do is we try to draw the rooms on this. We have a whiteboard, we draw infinite number of rooms on this whiteboard. Now, what does the inner product between the two states, if we define two states on this board as the cat of psi and the bra of phi, and we take the inner product of the two, the inner product will tell us that what is the limit of overlap that's taking place between one drawing and another drawing on the board. So this can be another way of understanding in day-to-day examples in terms of these cats and bras. And let's think about a city with many roads. We have a city, and this city is filled with roads in it, and this whole city will represent what's called as Hilbert space. Now, what is a Hilbert space? It is basically a mathematical abstract thing which has infinite set of vectors, infinite dimensions of vectors in it. And we can have a classical example if we talk about a vector, if we talk about the Euclidean vectors. If we have a vector R, it will have 3 coordinate vectors, right? But when we talk about the Hilbert space, in the Hilbert space, you can have the dimensions ranging from 1 to infinite numbers, and putting down that mathematically in an abstract way is what is called as the Hilbert space. And the cats and bras that we have been talking about, these cats and bras are basically the players of that Hilbert space. These cats and bras, they exist inside that Hilbert space, and once you make an operation on these cats and bras by making use of an operator, say for example, when we operate an operator on the cat, it leads us to have that information, the information that we are looking for in this Hilbert space. So what we have a city, and this city has infinite number. It has many roads in it, and each road is basically a quantum state. So the quantum state is over, as I said, the psi, the cat of psi, the cat of phi. These are the quantum states that are existing inside the Hilbert space. So you have a framework, a mathematical framework, what we call as Hilbert space, and within that Hilbert space, we have these cats and bras, the Dirac cats and bras. They are existing inside there, and each road is a possible quantum state, and moving between the roads, they follow these quantum states. They follow these quantum rules. Library can be another example to at least have the understanding of this mathematical abstract thing that we have in terms of the Hilbert space. We have a library, and in a library what we have numerous books in the library, and there can be books which are similar, and there can be books which are different, different to other books. And this whole library is an example of the Hilbert space, and the existence of these books inside the library is the representative of these cats. These cats exist inside that library in terms of these books. And if you take the inner product of the two books, the inner product of these two quantum states will lead us to have the information about the similarity of this kind of quantum states being present in that Hilbert space. So, in a trivial way, if we try to conclude our discussion here, what we say is that this Bra-Ket notation, what it does basically is, it basically simplifies the formalism, the Schrödinger formalism. It simplifies the quantum mechanics. And talking about the Hilbert space, This Hilbert space is the mathematical playground. It's a playground, and in this playground, you've got to play. These quantum states play. They play with each other. And these analogies that I have tried to code down here, they are giving us the abstract understanding of the concepts of these kets and bras. Now, if we move on from here, and focus on this, what we call as Hilbert, Hilbert space. Now let's get some understanding about this Hilbert space. And as I said, that this Hilbert space, it is a mathematical framework in which these cats and bras, they play and they give us the information about the system. So we can see here that a complete inner product space generalizing Euclidean space to infinite dimension. It's the more precise definition of a Hilbert space. So it's the generalization of the Euclidean space, the space of x, y, and z, or theta and phi, and it allows us to have infinite dimensions of the vectors present in that space. And this Hilbert space, what it does basically, it provides us a framework for studying the quantum states and quantum what we call as wave functions. And these four are the main concepts that are very much linked with this Hilbert space. The first thing is the inner product. The inner product that I was talking about, psi, phi, and the second thing is the norm, and the third thing is the completeness of these state vectors that are existing inside the Hilbert space, and the fourth important thing is the orthonormal basis. But before these four important conditions that can construct, that can build a mathematical Hilbert space, the very first importance of a space to be the Hilbert space is it should obey the linear vector algebra. Now, what does that mean? Your state, it has to be a vector. It has to follow the vector laws, and it can have a scalar in it, and this scalar can be of two types. It can be a real number scalar, or it can be a complex number scalar. So the very first condition about the Hilbert space is that there should be linearity in the vectors. Now, what does that mean? How we can demonstrate that thing? What we have is suppose I come up with defining the ket of zeta 1. It is a state vector, it's an eigenstate, and another state as zeta 2. And these two states, they should add up vectorially. So zeta 1 plus zeta 2 should lead us to another eigenstate, zeta 3. And these state vectors, they should be obeying the commutative behavior. So what does that mean? Commutative. So if I have state zeta 1 plus state zeta 2, this should be equal to the state zeta 2 plus zeta 1. And it should obey the distributivity and the multiplication of the scalars. And how we can demonstrate that to these state vectors is we can take on, say, I have a number, let's assume that number is alpha, and I multiply this number to the state vector, say zeta 1, and let me make this alpha common plus zeta 2, and this should be equal to a zeta 1 plus a zeta 2. So you can individually associate these scalars with these state vectors. So this kind of rule should be obeyed by the mathematical framework that you are leading towards the Hilbert space. Or if you have a situation like alpha plus beta multiplying a state vector zeta, and here you should be able to distribute them as alpha zeta plus beta zeta. So this is giving us the distribution of the scalars with the state vector. Another important thing is what we call as null vector. So if you have a null vector, if you have a state vector zeta, you add it with a null vector, you will get zeta. So what is important is that a Hilbert space, a space can be considered as Hilbert space if it obeys those vector laws that are true in a sense in Euclidean geometry as well. Now, moving on from here, what we have is we have been talking about this Hilbert space and trying to take down the different roots to understand it. And another way to give a line to this Hilbert space is a Hilbert space. If I assume it as H, it's a vector space. It's a vector space over complex numbers, and these complex numbers are equipped with an inner product. So you must be able to take the inner product between the kets, between the state vectors that are existing within this Hilbert space. And as I said, linearity. If I have an inner product of u and v with w, which probably we can write down is the inner product of u and w and plus v and w, reflecting the linearity. And as in conventional Schrödinger's picture, we have a wave function, we have its complex conjugate, and in a similar way, for an inner product that exists inside the Hilbert space, there exists its conjugate. It has to have that conjugate symmetry. That means if I have two states, u and v, then its complex conjugate should also exist, v and u star. And the positive definiteness, what we call as the norm, I mean, if we take the inner product of u and u, its value should be greater or equal to 0. And this is only possible if and only if the value of this u is equal to 0. And the next thing that we have here is what's called as the completeness. And completeness means that every function that you are playing with in a Hilbert space, it must have a nature of Cauchy sequence. I mean, what this Cauchy sequence is, to understand the Cauchy sequence in a mathematical abstract way, if I say, if I have something like, if I choose something like x, and this x is equal to 1 plus n. Now this n goes on. Now if this n goes on, so n is equal to 1, n is equal to 2 and 3, and every time you increase the value of the n, the overall value of the x, between the two values of the x's, the gap between the values of the x's goes on decreasing. So we can think about this function following what's called as Cauchy's secants. So if this n will tend to infinity, then the x will be fixed at a value equal to 1. And we can choose another example. Say I have a function, say fn of x, and this function is sine of nx by n. Now we can say that as this increases, as the value of the n increases, the value of f of n decreases. That means if I have another function m of n, the same function for the value of m as fm of x, the gap between fm of x and fn of x, it goes on decreasing at every step as you move on and on. As you move on and on, the difference between fm of x and fn of x goes on decreasing, and finally it completes. It has a completion at some point, and that completion is important for a mathematical thing to be the Hilbert space. So for being the Hilbert space, there is a need of that convergence of the mathematical function. The mathematical function should converge to a single shot at the end of its game. And we can think about an example. Suppose we have a ground, and there's a hell of fog in the ground, and in this ground there are two people, and these two people they cannot see each other. Now they are moving in this space, they are moving in the ground, they are not able to see one another, but if they manage to meet at a point in that hypothetical ground filled with the fog, then we will say that there is the completeness of the eigenstates in that Hilbert space. So what does that mean? That means the two persons being anywhere in that space, moving, and if the distance, for the sake of argument, because Hilbert space, it's not important that the Hilbert space carries only the information about the positions of the particles. It can carry the information about the momentum of the particles. It can carry out the information about other sets of the systems, observables, measurables that can be interpreted in terms of the Hilbert space. Now here we are talking about the two persons, and that means we are assuming that these two persons are acting as the state vectors. They're acting as cats and bras, and if these two persons meet in a fog, then we will say this makes this Hilbert space a complete Hilbert space. There is completeness. So what I said is that every Cauchy sequence of vectors, it converges within this hypothetical mathematical space, what is called as Hilbert space. So what we have, these are the important properties of this Hilbert space. The inner product should exist, and what this inner product does, it defines the angles and the lengths, and we must be able to calculate the norm, and it should precisely be invoking the property of orthogonality that I talked in the beginning of this lecture, that if you have two different eigenstates in the Hilbert space, they have to be orthogonal to each other, so that the inner product of these two states, so if we take these two states as u and v, their inner product must be equal to 0. At the same time, the inner product of the same state must be equal to 1. This one leads to the normalization, and this one leads to orthogonality between these two state vectors. And the completeness, I explained this, I tried to explain this completeness in terms of the two pupils being in a foggy ground and somehow managing to meet each other. And then comes the separability. The separability is the basis of the Hilbert space. I mean, the Hilbert space should be, it should be separable. What does that mean? That means that the basic building blocks of the Hilbert space should be finite. But out of that finite things that we have in the Hilbert space, we can manufacture infinite number of states. So this is what makes Hilbert space so beautiful, and it certainly has a very good connection to a day-to-day musical world. A world where we have the tones. Suppose if I talk about sa, re, ga, ma, pa, da, ni, sa, from sa, re, ga, ma, pa, da, ni, sa. So these tones can give birth to infinite number of rhythms, infinite number of states, infinite possibilities. But the base of all that infiniteness that exists in terms of the music is basically linked with those 7 magical notes. So with this, I would like to stop, and I hope that at least we are able to get an idea about the formalism, the Dirac notation, and the quantum mechanical formalism in terms of Ket's bras, and at least have an understanding of a concept that links us to understand what this mathematical formalism in terms of Hilbert space means.